So yes, we will see how natural language can be used to generate fake publication. And so I will present SCIgen, which is a tool that you can use to generate some scientific articles. And then we'll see how I've used it to create a fake scientist that had a very large H index. And then we will see how we can find and characterize this kind of scientific paper in large corpora, how to look for them. So I will present two tools that we will use for that. So intertextual distance and hierarchical clustering. It's very basic thing, so I guess you will have no problem to understand that. And then we'll go to automatically detect this kind of paper. And we'll see that there is some other kind. SCIgen is not the only one, there is some other kind of such paper. And complete. Okay, so Markov chain, I guess you all know that, or perhaps skip over that. Just you've got a learning phase where you learn the probability of changing from a word to another, and then you do kind of random walk to generate text. So this is quite known and used, so you can find on Twitter. So there is Le Singe, the monkey, who is tweeting in French, the brain, which is tweeting in English. So those automatic tweets are based on simple Markov chain, and they generate tweets. Sometimes tweets are meaningful, sometimes they are not. Most of the times they are not. And so here I've trained a kind of Obama bot who is trying to, well, he has learned on the State of Union addresses, and you can try on reproducing this kind of thing. So you can improve this kind of Markov chain generation using constraints Markov chain. So for example, the speech of address should start with something, should end with something. There must be some topic inside, just like we have seen for the Beatles. But I guess trying to make a speech for Obama with that, you will end up with plenty of junk, and a human reading that will catch it very soon. So if you really want to generate some text that can be read by human, you won't go for that kind of tools. You will more probably use what is called Probabilistic Context Free Grammar. So this is very simple. Maybe you are not very familiar with this kind of thing, so I will take a little time to explain you. So you've got a set of non-terminal symbols. Here we've got a sentence ended with a point, so SP, a sentence, a verb, and a phrase. And then you've got a set of terminal symbols, so the point, dot, and so a set of verb, like sing, dance, flight, sees, and then places, sees, oceans, etc. And then you've got rules, which are numbered, R1, R2, etc. You've got probability for those rules. And then a sentence with a point is a sentence with a point. And then a sentence is we shall, a verb in the place. Or it could be also we shall, a verb in a place, and then a sentence again. Or it could be we shall, verb in the place, and in the place, and then a sentence again. Okay, and then a verb can be one of those one, and a place can be one of those. And so you go through this grammar, and you generate what is called a derivation example. So I guess okay, so you know where this comes from. So we shall sing in the air and in the hills, we shall dance in the beach, and you can compute the probability of having exactly this sentence. And you can also have the reverse problem, so given a sentence, what is the derivation tree? So it's more often used that way, because this kind of tools are used to train, let's say, for translation or for lemmatization or things like that. Okay, so you are more trying, given a sentence, trying to find the most probable derivation tree. Okay, so if you want to write by hand this kind of grammar, you will have to be careful. So here I didn't say that given a set of rules having the same left-hand side, the sum here is equal to 1, okay? And so you have to be careful, because here we've got non-zero probability to loop and generate a new sentence again. You know, this kind of habit that have our computer to loop up to infinity. And so here, we call again a sentence S, and we call again a certain S with a non-zero probability, and so there is probability to loop, so you have to be careful. And also here, I've done a kind of little mistake in my grammar, because I've got an uppercase there that should be not here. So I should rewrite my grammar to avoid this uppercase, or do a post-treatment to remove this kind of strange stuff that are here. So writing this kind of grammar is a bit painful. It's a kind of lot of time, and you have to be very careful if you want the grammar to be respected. You have to be careful of inflected words and things like that. So with English it's okay, but I guess with a highly inflected language it would be very difficult. So well, this is time consuming, but still there are some people who have written a quite urge probabilistic context free grammar, and it's called SCIgen. And so its aim is to just write a scientific paper that has no meaning, but it looks like really the grammar is correct, all the words are fine, etc. So the idea is to try to enforce or to test the submission process of trying of strange conference and things like that. Okay, so the basic idea is that a scientific paper has a title, it has an abstract, an introduction. So this is kind of the first rule of the context grammar. And there is an evaluation part, and a related word part, and then a conclusion. Okay, fair enough, all the papers are like this. And then the conclusion, you've got starting conclusion, and then a closing conclusion, where you say in section 1, we will see in section 2, etc. And then introduction starts with sentence like many SCIgen people would agree that, etc. So as an example, I've put here a subset of all the sentences that can start a SCIgen paper. So you have here in blue the terminal symbol of the grammar. So for example, many stenographers would agree that, blah, 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 or serial informatician. So they have choose words that are quite unexpected, and so you end up with texts that are quite funny to read. So using this grammar, you end up with a really nice looking scientific paper. You've got a title, you can put your name, and you've got a nice abstract, you've got figure and graph. So this one is a bit strange, but you can have, if you are lucky, you've got a nice graph. And then you will have reference citing famous people like Turing and Newton and things like that. But you can also having self-reference to the author. And so, well, you've got plenty of paper like that. So you can generate them.
You generate the graphs as well?
Yes, he's generating random graph. No, not random graph. We've seen plenty of them. So yes, you've got nice paper. And so you can use them to test conference. So this is what they have done. And they were lucky enough, I don't know, to be accepted in conference in Las Vegas or something. So these were students from the MIT, okay, who did that. So they should have some time. You can do that when you are a student, I guess.
This is already also quite old, right?
It's 2005.
2005.
Yeah, almost 10 years. And so I've used it to create a fake scientist. So I will explain you. So first you have to know about the H-index. Do you know all about the H-index? Unfortunately, okay. So maybe you don't know that there is two different kinds of tools that can be used to compute this H-index. So the first are tool-based. They are not free. You can pay. You have to pay for that. So you may know the Web of Knowledge and Scopus, who are provided by a publisher. And so all the paper you will find in there are peer-reviewed, they are journal, peer-reviewed conference, and they are indexed by publisher. So you can imagine they have been really checked by editor, by publisher, etc. Okay, and by peer review. The other way to compute this kind of index is just crawling the web. So you can do it using mostly Google Scholar, and then you can build tools on Google Scholar that process all the citation numbers provided by Google Scholar. So Scholarimeter is one of them. Publisher Parish is the most famous. So if you want to build a fake scientist, you will more probably go that way. Okay, try to inject paper in Google Scholar to create someone that has agenda. So for that, you have to understand how Google Scholar is grabbing things on the web. As far as I understood, maybe you cannot very see, but I will explain you. So the way I understood, so this has been done in 2010, 2009, and so the way I understood it is that Google Scholar is including things if there are reference to real paper. So here there is some real paper, which are my paper, and I create a fake paper written by this fake scientist, and this fake paper is citing all my paper. So when Google will crawl it, it will insert it in its database. And so now if I want to fake, so I'm doing that, I'm faking my index, okay? Because I've got one more reference to all of my paper. And then if I want to create, with a minimum of effort, someone with a big hash index, I have to create this kind of complete graph here with 100 papers, citing all of them, also citing themselves, and they are all citing this paper that is going to be grabbed here. So when this paper is grabbed by Google Scholar, then at the next step, all this wheel here will be grabbed by Google Scholar. Okay? So in theory, this man here has a hash index of 100, or if you remove stat reference, only 99. Okay. So it worked pretty well, and I got this man here, Ike Antkare, who was indexed by all the tools that are working on Google Scholar. Okay, so he was indexed at quite high level. So yes, only here you cannot see, but it's only 94 of H index. So all the references that we grabbed at first. Then he went up to 100, and then went down to 30, and now he's at 0. So all the things have been removed. And so he was again above Einstein, but below Marx, and things you can compare. So you've got Garcia Molina just here, and well, you can compare your scientists to other great scientists. So well, what does that say? It said mostly that that's what people were saying. So Google Scholar, it is very complete because you grab all what is on the web. The accuracy, you don't really know because you don't know how it's really doing things, but well, fair, it's good enough. And on the average, something like that. And then for the WOC and Scopus, it was said that this is quite very incomplete because if you are not in the field, some of these tools are good for biology or medicine, but for computer science it's not so good because it's not complete and things like that. And about accuracy, well, it's more or less error-free because things are checked very well, and you can even connect there and see if there is some missing reference that you know to your paper. And you can say, yes, this reference is for my paper, etc. So by hand you can check and add things. And so the robustness was considered as excellent because you cannot put things here that has not been checked. Okay? So mostly what the experiment before say, so you cannot see, but you can span Google Scholar. You can put things in there fake it, to change the result. So the question is, are also woke and Scopus and fee-based tools really error-free and with an excellent robustness? So to answer this question, we need some tools to analyze big corpora and try to find out what the property of the paper in there. So I'm going to present two different things, intertextual distance and hierarchical clustering. So to compute intertextual distance, we will just consider text as what we often people say bag of words, okay, no order, just counting thing. So here, for example, I've got two texts, and then I will consider those texts as being points in a high-dimensional space, which is the dimension of the number of different words there is in the text. So for example, here, there is three different words. There is chat, there is un, and there is le. So we've got a three-dimensional space, and we've got 2 points here. So this is text A, and this is text B, and you can place them in this high-dimensional space. And if you want to compute the distance between these 2 points, you will use, or you will not use the Euclidean distance, usual distance. It has been shown that it has not so good results with text, so often people don't use that. People from information retrieval are often using the cosine similarity, okay, which is the cosine of this angle here, the angle between the two vectors, because it has been shown to have good results, good accuracy, good definition, etc. So people are often going for that. I will go for another one. We call it intertextual distance. It's something like more kind of Manhattan distance. So for example here, we've got 2/3, and then 1/3, and 1/3, so that's 4/3. If you divide that by 2, you've got 2/3, and 2/3 is exactly the number of words that you need to change to go from that text to that text, okay? So this is really, for us, this is really a kind of natural distance for text, okay? So this is a distance that has meaning, really, on the text, on frequency on the text, okay? Usually we don't compute it on well, you can see in the paper we compute it. We are working on absolute frequency, but still it's the idea here. And for us it is really highly interpretable. Highly interpretable because if you've got the distance of 1, this means you have really no word in common, okay? So this is 2 different languages, okay, no word in common. If you have a distance of 0, this means that all the words are the same and used at the same frequency. So it's not really mean that this is the same text, but still, if you've got text long enough, if they are the same word at the same frequency, this really means that they are the same, okay? Well, and if you have another distance, this gave you the proportion of words that are different in the 2 texts. If you pick 100 words in text A and 100 words in text B, on average, you will have this number of words that are different, okay? You can also see how this distance will vary. So if you have a very short text, the frequency won't converge, so you will have high variation that you are not really able to explain, okay? But if you've got text long enough, this distance will be influenced by the authors, your habits on using words, the topic, the genre. You will not have the same distance if you are doing poetry and doing prosody, and the epoch, because as we have seen, we are not using the same words at the same epoch. So really, you can see kind of scale here. So if you've got low distance, you've got the same author and the same topic. And as far as you are increasing the distance, you've got different topic but same author, or same topic, different author, for example, and things like that, up to a different language going to 1. So this distance is quite highly interpretable, and you can take a kind of big bunch of text and try to see the distribution, and then you will have a really a kind of Gaussian that will be centered about around 0.6 or something like that. It depends.
So sorry, are you removing stop words?
So you can do, I think this is kind of pre-process that you have to do. So you have to decide before using this kind of thing if you are working on stop words or removing stop words, or if you are trying to work on lemmatization, path of tagging and this kind of thing. So the results you get is highly dependable of what you are doing before. Okay, so usually my dad is working really carefully and is always lemmatizing. What exactly? It's text in French, often. And because he considers that you cannot count things that are not the same on the same thing. And that's what you are doing when you are not lemmatizing.
But my worry was more that I think the most frequent words will dominate this measure.
Because you've got plenty of words. You've got some small, you've got a small amount of text of words that are frequent, but you've got plenty of them that are not frequent. Remember, it's one over f.
But if you count tokens, the tokens dominate. So the most frequent words dominate. Well, anyway.
It's not they. I don't. We did some measure to understand how their weight was in this measure, but so yes, they are counted here, but they are not so.
But you're saying that it's not significant somehow.
It is significant, but we want them to count. Okay, so we want all of the token of the word of things to count. And here I will use it in a very brute way, because as you will see, I will just count token, and so a very dirty way to use it. So here we don't have this problem. So then I will use hierarchical clustering. So okay, so I will go. So you are trying to cluster things that are that must be together. So first you cluster those two texts because they are the closest, and then these two one because they are the next to be closest, and then again you aggregate those two clusters, and you get this kind of diagram. You have to read it like there is no order on the x-axis, but here you can see the height at which the text has been clustered. Okay. So now we can compute the distance and do the aggregation, and we collect the big corpora from different bibliographic base, and we try to see what we can see. So here you've got the acceptance rates of the conference, the corpus size, and we will add 100 texts from SCIgen, and so extracting PDF without the reference section, and compute the distance matrix. So on what has been coming out from the extraction, so it's very brute, very dirty. And we build a diagram. So I don't know if you can see, but so you've got plenty of color here. The one that is important is black one. This is fake text, and what you've got is here 4 real texts that has been published in a conference that announce acceptance rates of 28, and well, they've got 4 fake here that are clustered in this fake group, and here we've got 2 texts that are exactly the same. In fact, only the title is different. So it was same text except twice in the same country. Okay, and so this was in IEEE. This was also in Scopus, Web of Knowledge. So you can wonder, how can I find some more? So we use more like this button that was in IEEE at this time. So when you click on, so you select a fake paper, and you click here, and you get 100 of new paper. So the question is, are they all fake or not? So we click 3 times here, so we get 300 paper, but out of the 300 paper, only 122 were different. Okay, so clicking 3 times, we get 122 papers. And again, we do this dendrogram. So you cannot see, but here there is the fake paper with plenty of red paper in there. And you've got also some red paper here. So this means that more like this function is not working very well because you don't have only fake paper, you also have real paper in there that are clustered here. But you also have got plenty of fake paper over there.
Published.
Rubbish.
Published.
Published in real conference, in IEEE conference. Okay. So how is it possible to detect them automatically? Okay, here we don't detect them automatically, we just see them on the clustering graph. So the question is it possible to screen the database and remove them? So for example, to Google Scholar, to remove them for the computation of the hash index, or for those carrying IEEE to avoid having this kind of rubbish and selling this kind of rubbish, okay? So I skip a little bit. But here you can see this fake is sold at the price of $20. Okay, so you can try to do plenty of learning thing, okay, machine learning stuff to classify this kind of paper. So this is what we have done. A very simple one, which is the nearest neighbor classification. Okay, so 2 class SCIgen paper, genuine class coming from computer science, and you classify the text. If it's close to a fake, it is a fake. If it closes to a genuine text, it is genuine. Okay, or at least it is non-SCIgen. Okay, and to assess this method, we took some more corpora. One coming from Arxiv. Do you all know Arxiv? Okay, no? Yeah. Okay. So there is quite plenty of text there, and we generate some more SCIgen paper. Meanwhile, I found a SCIgen physics. So this is a clone of SCIgen, but generating paper for physics. So it's a kind of neutral thing. I don't understand anything, but it has no meaning, so it's all right. And so I generate paper from these 2 tools. And with these 2 corpora, I'm trying to estimate the misclassification risk. Okay? So all the paper from the first SCIgen and from the SCIgen physics were very well classification. No problem with that. And with distance that are really quite low. So that's okay. And the risk of this one is more bad, because if you classify a real paper as being a SCIgen, it can be, you will accuse people to have done rubbish, and they are not. So you have to avoid that. And so 8 texts were wrongly classified as fake, but they were not all non-English. So with the distance very high, near 1. So this is kind of bad luck, because your training set is not adapted. So you should try to change your training set if you want to avoid that. And here we had another thing that is quite embarrassing. We take a decision at a very, the third decimal is only 1 difference, and so we fall in the wrong class. Okay? And the distance, again, is quite high. This is a paper that is not really computer science. It's more about learning, human learning stuff, and it's using computer science, and it's a kind of ending project document. Okay, so to be compared to what we have chosen as the real class. Okay, so that's why this kind of thing for me is not really adapted here, and we went for something else that just deciding that if the distance to the fake is too much, okay, this just means that this paper has not been generated by this tool. Okay, so this is the way this little website is working, and so it is quite used, and well, we have been able to catch different things there, and this is really working like a bit kind of touchy attribution, because if the distance is too high, you just say that this is not from this author. Okay, the generator is really behaving like an author that would have a very restricted vocabulary and very strong habits, repeating things, etc. So you've got very texts that are very clustered all together, very similar. IEEE and Springer, so the result of this experiment, so IEEE and Springer, IEEE more than 100, Springer a little bit less than 20, have published and were selling completely fake paper. And at the opposite, there was no SCIgen paper in the arXiv repository, which is an open repository. So this is quite amazing. And when the matter became quite public, I got a mail from Gene Spark, who is the one who started arXiv, and he said, well, at that time there was kind of cursory glance to accept paper in the arXiv database, but now the rate of submission is too high, so they are not able to screen, like even a cursory screening of all the papers that are included in arXiv is not possible. So it turned out that they have their proper screening phase before introducing paper into the repository. So here is a little test he has done. So he's working in a different way. He's taking only stop words, so he's not removing them, he's only keeping only the stop words. And he's doing so this is a principal composite analysis, okay? And you can see here all the real paper, and there all the fake that are coming from SCIgen. And here you've got another cluster which comes from another generator which is doing math. So this is MathGen, okay? So the question here is, are probabilistic context-free grammar unwritten always detectable like this? Because frequency would be weird and you will always be able to catch them, okay? We don't really know if it's possible or not. So, yes, here you've got a new class of generators that pop up, okay? So maybe there will be some more as the time is going on. So I had also a kind of mixed, so this was submitted on the detection website. So it's a mix of plagiarism and SCIgen. So here it will be clustered, it has been clustered as SCIgen, but you can imagine that if the paper contains only one paragraph of SCIgen, then the distance to the other SCIgen paper, pure SCIgen paper, will be quite high. And so it won't be classified as SCIgen. But I would say, well, fair enough, it's normal. It's not really SCIgen. Only a part of it is SCIgen. Okay, so if you want to detect a little chunk of text like this, it's a kind of different way to, perhaps Mirko will be able to catch this kind of small bunch of text. No, okay. And so this is kind of thing that can happen, so mixed of real paper and fake paper. And so this is a new generator that popped up in 2012, I think. So it's mathematical stuff. So it just exactly is like SCIgen, but doing mathematics with really big formula. So I've tried here to classify, to show you real paper, SCIgen paper, physics paper, MathGen paper, and that's another one to generate ground proposition. Okay. So, but that one is really quite bad. Telling is always giving quite the same text. So it's a really quick thing that has been. And so they are all well classified. Okay, mostly because the statistic properties they have is quite weird compared to human. Okay, that is here, and they are too restricted, so they are grouped together. But if we add here the Obama speeches and the text from the Obama boat that we have seen at the beginning, they are clustered together. Okay, because the Obama boat that is generating text using a Markov chain will have will have good frequency compared to those true Obama speeches. That's why they will be grouped together. So my detection system will be paced or will be tricked by a generator that is mimicking the frequency of human text.
Because you're using bag of words.
Because I'm using bag of words, because I'm only using frequencies. Okay, so as a conclusion, so we found quite many fake. The explanation for that is mostly, trying to understand it, is mostly done by the publisher. And I've set up little websites where you can submit a bunch of PDF. You submit a zip file with plenty of PDF there, and the website decompress it, extract the text, and show you down the ground, and for each text it has been classified as SCIgen or not. And so it started to be used automatically by some publishers, and so I've got quite plenty of rubbish there. And so you can ask yourself how you can automatically detect this kind of generator, because I'm detecting them only if I have example of this kind of generator. Okay, so how to detect them automatically? I guess you will try to find dense cluster inside population. Okay, so if you find kind of really dense cluster there, you can ask yourself if there is kind of generator there. And so here we've got kind of two different things. So with unwritten context-free grammar, they are grammatically sound, but statistically they are not human. Okay, in the sense that they are having strange things. Ginsparg thinks that even the distribution is not Zipfin. Okay, so I didn't check that, but it could be quite easy to check if the distribution of words for this context-free grammar are Zipfin or not. And so if you use kind of Markov chain thing, you will have something that is not human-looking for human, but that is more statistically sound regarding human language. So, thank you very much.